So, dann geht's auch gleich weiter. Der nächste Vortragende ist David Bowman, Golf Zero Mike Radio Fox. And the title is Jovian-1 and FUNcube CubeSats. You are welcome, and this is your microphone. And this is your presenter.
Okay, thank you. Guten Tag, AMSAT-DL. This is my first visit to Bowman, and I must say this is a really impressive facility. I've seen so many pictures of it online. It's a real pleasure to be here, so thank you for the invitation. I'm here today to give you a brief update on some AMSAT-UK projects. Essentially, we've got two satellite projects underway at the moment. The first is FUNcube Plus, which is a 2U CubeSat, essentially a follow-on from AO-73, the original 1U CubeSat we launched in 2013. That's coming up to its 12th birthday in November, so it's doing very, very well. And of course, we have to look into the future and try and find something to replace it. FUNcube Plus is underway. It's been running for a while. We've spent a lot of money investing in components for this particular project, but it's not the one that has our immediate attention. We're currently working on FUNcube Lite. It's a payload on a University 6U CubeSat in the UK, and it's called Jovian-1. But before we all get excited, it's not going to Jupiter. This is definitely low Earth orbit. A curious name. So let's start off a little bit before we look at Jovian-1, which is going to be the main topic of today's talk. We'll have a look at that FUNcube Plus project and see what we've got in mind for the payloads. As I say, it's a follow-on to AO-73, but we've doubled in size to a 2U structure, so 20 centimeters by 10 by 10. The idea is that we will repeat some of the functionality from AO-73 so we can retain things that we know work, and that's going to be the UV linear transponder, UHF to VHF, with BPSK telemetry for educational outreach, providing all the usual data sets from the satellite's health. We're also going to include, as part of the plus on this mission, an L-band L-band to VHF transponder, because as I've seen yesterday, one of the comments in the GEO workshop is unless we use the bands that we have as radio amateurs, we are going to lose them. And I think 23 centimeters is already under considerable threat. I believe here in Europe, the recommendation now is that we only get to occupy a small fraction of what was originally allocated. We originally had 1260 to 1270 megahertz for amateur satellites, and I think that's now down to 1260 to 1262, with some very serious limitations on ERP because of the global positioning systems that exist on the same frequency band. Fortunately, one of the very small benefits of Brexit is that we were thrown off the Galileo project by our European partners. And so at the moment, I think the UK government isn't too bothered about implementing those restrictions on 23 centimeters. So at the moment, our regulator, Ofcom, is saying we're not complying with those regulations yet. So we still enjoy the old power limits and frequency designations for that band. But L-band to VHF, I think, is something we do need to put up there just to make sure we can say at all of these international meetings, we actually are using this band. Also, we're going to add a camera for still images. Hopefully, it'll be a fairly high resolution camera. And the idea of that is that we are looking at a QPSK downlink around 18 kilohertz wide. Now, this won't be constantly sending that signal down because taking up 18 kilohertz of the 2-meter band isn't a terribly friendly thing to do. So every now and again, we'll switch that on, take some pictures, send those down over several orbits, and we're going to implement a system where the blocks reflect a small portion of the image, which will be built up over time. The more blocks you receive, the more parts of the image will appear on your screen. And of course, with all of the internet connectivity, there'll be a server somewhere picking up those images from all of the people who have receivers picking it up and assembling the image on a central server, which can be visible to all. AO73 is currently rotating every 4 seconds. And earlier this year, it was up to about 2.5 seconds per revolution. That's completely incompatible with a camera. So what we've done is we've purchased not exactly 3-point axis control, but we've purchased an attitude stabilization board, which we know from previous use. It's got magnetorquers on it, and it can actually stabilize the satellite. Point it roughly in the right direction, which is what we want, but it's not a full attitude control system as we would normally expect. But that should help us take pictures very successfully. What do we already have? Well, we have a structure. We have the magnetorquer board for attitude control. We have a lithium-ion EPS from ISIS-Space. UV antennas from ISIS-Space as well, and a complete set of solar panels. We've actually got just 5 solar panels on this. If you can imagine, we've got the 20-centimeter ones all around the outside of the structure, and we've got one single panel on the bottom. The other end of the satellite will have the camera and a deployable L-band antenna on it. So we're working on that, and we've cleared the space of solar panels to implement that. Major issue, licensing. We look at envy at AMSAT-DL and other people in Europe. The UK government are still living 20, 30, 40 years ago and think satellites are all the size of a London double-decker bus, and at some point they're going to fall down through the atmosphere and crush somebody's house. Because of that, they insist on every satellite, no matter whether it's a pocket cube or something the size of a double-decker bus, having an insurance indemnity of £60 million. And I can tell you that the current insurance premium for that is £28,000, and that's payable annually. So licensing in the UK is definitely off the table. Also, our current satellite, AO73, is licensed in the Netherlands, who take a much more pragmatic approach. They actually assess the risk. But even now, with 8,000 Starlink satellites, and we get conjunction warnings sometimes 4 times a week, the insurance premiums there are creeping up, and that's currently up to €10,000 annually. But at least it's a third of the UK. So, if your country has no insurance requirements and you would like to buy a fully functioning 2U satellite with a check for the launch, come and speak to me later. Okay, current priority then is Jovian-1. Let's have a look at that in more detail. So FUNcube Lite on Jovian-1, as I say, it's a 6U university CubeSat. We've got the University of Southampton, University of Portsmouth, and our old friends at Surrey University from days go by. They've still got a very active satellite engineering facility there, and the satellite's currently undergoing integration in their clean room. There's an image up on the top right there of what it's intended to look like. Typical 6U structure. But as you can see, they've gone a bit enthusiastic with the power budget. There's that rather large deployable solar panel. It's 0.9 of a meter long, so 90 centimeters long, and what would that be, 20 centimeters across. So if that deploys successfully, I think we have something like 45 watts of power available. The antennas on there are 3 different types of antennas on there for the commercial use. At the back on the right-hand side, you can see a little sticky out thing. That apparently is an omnidirectional S-band antenna. If you can imagine, it's only going to be omnidirectional with certain limitations because it's got the 6U structure right in the way of it. But in the early launch, on the LEOPS phase of this, that will be used to establish contact with the satellite and ensure that it's got the correct degree of attitude control. On the front there, we've got 2 patch antennas. These are commercial band, S and X band, S band for up and down links, and the X band for higher speed data. So, Jovian-1. Why would you come up with a name like that? Well, acronyms are everything. And somebody at the University of Surrey created Jupiter, Joint Universities Programme for In-Orbit Training, Education and Research. So a very nice name, and the first mission for this programme is Jovian-1. Launch of this project in a sort of getting started method is, if you have a look on there, fortuitously, exactly 1 year ago today. So this project kicked off on the 20th of September 2024, and here we are to the day a year later. A somewhat sagging in gravity model of the satellites down there on the bench in front of the students, but it's actually taken a bit more of a real format over the last 12 months. So the satellite itself, before we look at the AMSAT-UK payload, is a 6U satellite based on GOM-space structure and avionics, 3-axis stabilized, single deployable solar panel, 45 watts maximum power budget, 5 payloads on board, 4 from the universities and 1 from AMSAT-UK, S-band omni and high-gain antennas for up and down links, X-band downlink for higher speed data, and the satellite uses CAN bus communication. Short project timeline, delivery for this is around December 25. I say around because timelines always shift, and it shifted a little bit since we first started. So here we have a CAD image. The original picture we saw didn't show the AMSAT antennas on this. At the moment, we can see the satellite is Earth-facing on that far side. We've got a few solar cells on the space-facing side of the satellite, and the antennas we've included here are a UHF dipole that deploys in either direction, and a 2-meter monopole that comes out facing space. Of course, that monopole needs the solar panel to deploy because it's going to work against Earth. So if you imagine the quarter wave monopole is 0.5 meter in length, it needs that 90 centimeter solar panel to come out to actually make the matching work as well as it can. So the payloads then, student imaging payload, taking still images and video, combined effort by students from the 3 universities. An experimental dark matter detector from the University of Southampton. That's an intriguing one. Space radiation monitor, it's a new radiation detector designed by the Universities of Surrey physics team, and they want to test that in space. And a tiny machine learning payload from the University of Portsmouth. I guess we could think of this as AI. Is going to read data from some of the payloads and try and spot patterns and predict results while it's on orbit. FUNcube Light, educational outreach and communications, of course, by AMSAT-UK. We like to see lots of dishes, and following on from Dwingelo and being here at Bockham, I can't do as good as that, but we have a 3-meter dish at the University of Surrey for the S and X band downlinks, 35 dBi on S band with a beam width of 1.6 degrees. I have no idea what the beam width is on 10 gigahertz, 8.4 gigahertz, but it's going to be a challenge to find the spacecraft, I think, in the first few orbits. This is the feed, which I think was built in Holland under contract. It's essentially a circular waveguide feed with probes coming in at 90 degrees. You can see the larger diameter on the left-hand side there is the S-band, and you can see the locations for the probes going in at 90 degrees there, and the inner waveguide section is for 8.4 gigahertz. So FUNcube Lite then, functions of that, BPSK telemetry for educational outreach, our standard 1200 bits per second with forward error correction. It'll include health data from FUNcube Lite. I think we've got 12 sensors on there. And also reading things from the CAN bus from Jovian-1, so we'll be able to downlink data from that as well. Hopefully things like Magnetorquer data and some of the things we wouldn't normally have access to on a single CubeSat. For the communications, we've got UV already coordinated with the authorities. Uplink 435.090, 67 Hertz CTCSS, and it has a 10-second timer. So if you can get in 150 milliseconds or so of signal, it triggers a 10-second timer, which means that the transmitter stays on until it times out. BPSK and FM downlink both use 145.895, and the way we see this working is that initially the amateur payload will be on during eclipse, and during the illuminated part of the orbit, we'll concentrate on getting some data down from the satellite. Power-saving modes are included as usual with most of the things we do. When we did AO73, we were almost paranoid about power budgets. So we have the ability to autonomously change at eclipse entry and exit, so we can go to a power-saving mode in eclipse. We can also do orbit counting, so it's possible to be on for one orbit and then off for the next, all with an idea of making sure the satellite actually continues to work. We provide Windows-based ground station software. If anyone's got the software package for decoding telemetry from AO73, it also dealt with Naif-1 and JY-1 from Jordan. And we have an online data warehouse which aggregates all of that data and stores it for future analysis. So what have we got? Well, one of the things we thought we would put on is exactly the same radiation detector that we've spotted in one of your pocket cubes. We've got a BG51 radiation detector. And then the university said to us, oh, we're not sure about the electromagnetic compatibility of your payload with all of our science payloads. We want to put it in a screened box. So we've got a radiation sensor that's sensitive to beta radiation and others. And it's inside a screened box, which will probably stop most of the beta radiation. So that's an entertaining one. But at least it will give us an idea of how good the screening is and how much radiation there is in LEO. We've come up with a 4-board solution. 4 boards, the VHF-UHF communications, a separate VHF power amplifier, command control and telemetry, and one that we enjoyed calling Cannibal, which is CAN interface board for AMSAT Lite. Stack height is about 0.6 of a U, and of course we needed some antennas. And we bought one of these at great expense from ISIS Space. They may be expensive, it's the company's best-selling product, and they hardly ever fail. Never been known to fail. We've got 3 of the 4 points loaded with antennas. We've got a UHF dipole there in 2 parts, all curled up, ready to go. The element is some form of memory metal, which is quite good. And the VHF one is on the side here, so it comes out in the direction of the left-hand side of the screen. That's actually an image of the bottom end of the 6U CubeSat taken in the Surrey clean room. So this is coming along at a fair old pace. Nice thing about this particular deployer is it's only about 5 millimeters thick. So you can put that onto the bottom of the CubeSat and then still have space for a set of solar panels once you've put the cover on. And if we have a look at that, you can see it's 98 by 98 millimeters, but it fits very nicely on the bottom of the CubeSat there. And although there won't be solar panels on this one, if you use one of these on a standard CubeSat structure, you can put solar panels on there, so you're not wasting any space. So when you start one of these things, you want a basic idea of what needs to connect to what. So there's a block diagram of system connections. Left-hand top is the antenna deployment system from ISIS-Space. The other 4 boards are ones that we have to provide. And then we've got a harness connector down there on the right-hand side connecting to the CAN bus. 28 volt supply. It's actually 26 to 33. It's 18650 lithium-ion cells. So it's 8 of those in series on the satellite, together with regulated 5 volt and 3 volt supplies. Our boards all talk via I2C. The main satellite talks in CAN, so most of the work at the moment is going on the software to get those two things talking to each other sensibly. Let's have a look at the boards. This is command, control, and telemetry. We've got I can't remember who, it's a Freescale CPU down at this point for doing most of the telemetry generation, telemetry collection rather, via I2C. The larger chip above it is a CPLD from Xilinx. We found that extremely good as an architecture, because if the microprocessor fails, we can still send commands into that Xilinx chip and command the mode changes on the satellite. So we can have an awful lot of that die, and we've still got a functioning satellite. As an example of that, JO97 from Jordan. We think the microprocessor on that board has failed, but it's still perfectly controllable in terms of its modes, because we have this effectively piece of hardware sitting there connected to a command decoder. Okay, this is Cannibal. Not much on this one. You could almost get this on a pocket cube, I think. We've got an STM32 in the middle there, which does the talking to a CAN transceiver. So that takes in data from the satellite and converts it into I2C to be joined onto our system. We've got a BG51 radiation sensor, because we had the space on the board to put it. And I think the only other thing, top right-hand side, is a switch mode power supply to go from 32 volts down to 8.6 volts for our VHF power amplifier. Transponder board, I think you could call this a legacy design. Some very well-known parts on that one. Fairly component heavy. There's probably 300 components on both sides of that board, well, in total. But it works very well. It's flown on a lot of previous missions, and we've simply combined a couple of boards together for this particular payload opportunity. The PA board is still based on the Mitsubishi RDO2 MUS1 FET. We've biased it at a measly 20 milliamps, and that seems to be perfectly okay for linearity. We've had those running on several satellites over many years. It's done about 26 years in low Earth orbit, cumulatively, without failure. So we're very pleased with that particular piece of technology. On this particular board, we've increased the number of inputs by adding a mini-circuits combiner. So as opposed to just having one input on 2 meters, we can take in signals from other boards. if we need to. That will feature on FUNcube Plus and some other satellites in the future. On the back is, I think, a minimalist implementation of an FM transmitter. That's a Silicon, well, Silicon Labs is now Skyworks, I believe. That is a Silicon Labs 550BE. It's a voltage-controlled crystal oscillator. You order them from Skyworks if you convince them you are a worthy cause, and you get it programmed onto the frequency that you want. It's essentially a microwave oscillator and a whole barrage of DSP functionality. But it does give you voltage control, so it lands you on the frequency you want, and you wobble the control voltage to apply FM. And as you can see, there's probably not 20 components around it, including all the filtering that goes ahead. So that's a very nice implementation. Minimum component count, disadvantage oscillator phase noise, and you have to make a judgment whether or not that's acceptable. So here's a spectrum of it, and as you can see, outside the bandwidth, the noise level is down here, and as we approach the middle of the transmitted signal, we have an increase in phase noise. We looked at it. It's about 45 to 50 dB down on the peak signal. We deemed that correct, considering the advantage that it gave us. Little look at linearity. For the BPSK, we obviously need the linear part of the curve. So that's the transfer function for the BPSK telemetry. On FM, we push that a little harder, but we're not too worried about how far up that curve or how flat it gets. And of course, being radio amateurs, we have the ability to take things to the top of a hill and actually use them in practice. So you see all these wonderful measurements in a lab, and you think, yeah, but I wonder if it really works. So we replaced the onboard computer with a few switches, the power supply with a box of linear regulators, and we drove to the top of a hill. In the back of my trusty German VW. And on the left-hand side, you can see the 77 receive antenna is a QFH made at home. So we had that on receive, and a vertical mag mount on the car for VHF transmit. And we found somebody who lived about 60 kilometers away. It was a slightly obstructed path. And when we measured the path loss on a prediction profile map, we found it's 150 dB path loss. So if it worked over that, it was going to be pretty good. And we found that the chap could access it with about 3/4 of a watt, but admittedly a beam antenna on 77s. So tested over 60 kilometers with a few QSOs thrown in just for fun. That's a picture of the satellite being integrated. Up near the top left-hand side, you can see some reaction wheels, part of the 3-axis stabilization system. The components on this side, the lower part of the photo, are the communication modules from GomSpace. And the empty spaces, of course, are awaiting all the student payloads as well as us. But hopefully, this will be completed and environmentally tested and ready to go by about the end of December. I hope that's the case, because as with all commercial projects, when the money runs out, you haven't got anyone to run the clean room or manage the project. So a very tight timeline. Okay, any questions? Thank you very much.
Okay, David, thank you. And yes, any question for David? No question. Okay. Thank you, David. And this for you. Very much. Okay, applause for David.